And let's just review some of the basics of the metric system together. This, of course, starts on page 4 of the lab manual, where you have some of the basic information about metric conversions and scientific notation. What I'm showing you here are just some of the basic metric units that we'll be using. The SI units referring to the International System of Units. In terms of physiology, these would be good bases to use. Right. These are our default measurements for distance, mass, volume, and temperature. For distance, the meter. For mass, grams. Volume, liter. Temperature, we typically use Celsius in physiology. In terms of SI units, there's some differences there. Meter is still the international unit, right, for distance. But then for temperature, for instance, the international unit is actually Kelvin rather than Celsius. Just some examples of the differences there. What might we use for a standard unit or a base unit for time? If we needed to, say, measure the reaction time or the time or duration of an action potential, for instance, what might we use as the base?
Millisecond.
Okay, millisecond, but give me the base of what that would be.
Second.
Not so, all I need is the word, right? Because milli, right, is the prefix for that base. So what is the base?
Second.
Second, there we go. Right, second. So second would be the base unit. But yes, if we were measuring the duration of an action potential, we would need something smaller than a second, right? It would be more relevant if we use milliseconds, use that, that prefix, for instance, which brings us then to the prefixes we would use for these orders of magnitude, being able to measure much larger than our base unit and much smaller than our base unit. So here are prefixes, and we can plug in any of those bases. We can plug in our liter here. We can plug in our second here. Right, this denotes the base where I have the little dashed line. What else did we review? Distance would be meter. We plug that in there, right? You know, you can even use Celsius if you wanted, plug that in there. But these are the basic ones that we would be working with. What I'm showing you here on the screen, do you see the green highlight on the screen? From here to here, where we go from kilo to femto. Those are the orders of magnitude that are important for physiological systems for the most part. And that's what we're going to focus on, is being able to convert back and forth within the metric system all the way from kilo to femto. So let's take a base here. Let's use liters. No, let's use meters. Let's use distance. Okay, so there's our base. Here, if we say deca, which is oftentimes written as CA as well, oftentimes with a capital D to denote that it's greater than our base. Deca means that we have 10 of those meters, decameters, right? If we're talking about hectometers, well, now we have another order of magnitude, right? Difference, 10 times 10. Now we're talking about 100 meters. And then typically we use the capital K here, just to note that, once again, kilo is larger than our base. Kilo would tell us we have 10 times 10 times 10 meters. We have 1,000 meters in 1 kilometer. I'd say that's the easiest going from the small to larger, going from the large to the smaller. Well, there's many more prefixes to remember here. And now we're talking about fractions of a meter, right? So when we say a decimeter, we're talking about 1/10 of a meter. There are 10 decimeters in 1 meter, right? 1/10 of a meter. A centimeter is 1/100th of a meter. There are 100 centimeters in 1 meter. So when I say that, that gives you your conversion factor, knowing that you have 100 of those centimeters in 1 meter. Milli, how many millimeters are there in 1 meter? Throw it out there. 1,000, there we go, 1,000 millimeters in 1 meter. How about micro? How many do we have there? How many micrometers are in 1 meter?
100,000.
1 million.
More than 100,000.
1 million, sorry.
1 million, exactly. When we say micrometer, we have 1 million micrometers in 1 meter. So look at the scientific notation we use here for micro. Go out to here, -6, 6 decimal places. 1 micrometer is 1/1,000,000th of a meter. It's the fraction, 1/1,000,000th of a meter. Okay, so if a micrometer is 1/1,000,000th of a meter, what nth is a nanometer of a meter?
Brilliant.
A billion. 1 nanometer is 1/1000,000th of a meter. There are a billion nanometers in 1 meter. Okay. Pico. How many picometers are there in 1 meter?
1 trillion.
1 trillion. Awesome. There are 1 trillion picometers in 1 meter, or we can say that there are, or we could say a picometer is 1/1,000,000th of a meter, very small fraction of that distance or that length. And then femtometers.
1 quadrillion.
1 quadrillion. Perfect. 1 femtometer is 1 quadrillionth of a meter. There are a quadrillion femtometers in 1 meter. That's the level we're going to here. So when we say picometer measurements, pico or femtometer measurements, when might we be measuring something that small? Generally, we're not using distance measurements if we're talking about physiological systems, but we might be using that for volume measurements. Picoliters or femtoliters, when we're talking about very small amounts of hormone that might be released in the body fluids, and measuring those concentrations within your body fluids. We might need to use picoliters or femtoliters to measure those small amounts.
What about for hemoglobin?
What do you use for hemoglobin?
Yeah.
For the measurements of the amounts, you can use picoliters. Or sorry, picograms. I forgot grams there, didn't I? I should put, there we go. Let's not leave out grams. Usually we're measuring the mass, but we might measure it in picograms if we're measuring the mass of hemoglobin, typically in 1 red blood cell, because the amount would be so small. So with metric conversions, in your lab manual on page 6, I believe, that page begins with what's called the dimensional analysis, which is the way that we can cancel out our units, right, in order to convert within the metric system. In order to use dimensional analysis to do this, this means we need to know the conversion factors for our metric system. We need to know that there are 1,000 milligrams in 1 gram. We know that there are 10 deciliters in 1 liter. We need to know those facts in order to use this method to do the conversion factors, right? And so let's just practice a few here. Just some easy ones, so we can see how this type of dimensional analysis that you've probably used before in other classes. I think now they sometimes refer to them as train tracks in the way they draw them. I use the old-timey, old-fashioned way of writing out my dimensional analysis, but you'll get the same idea and same information here. If I had to convert my 34, excuse my writing on the screen, I'm writing upright, 34.5 centimeters to meters, right? In the end, I want meters. What conversion factor would I use there? One meter is how many centimeters?
100.
100 centimeters, okay. So I know that 1 meter is 100 centimeters. In order to cancel out centimeters, so that I'm left with meters, do I put my 100 centimeters on the top or on the bottom?
Bottom.
Bottom. So I have 100 centimeters in 1 meter. Now my centimeters cancel out. Okay. And I can use my calculator, and I would get 0.345. Okay. Now, I'm not saying you have to use this method. If you have a quick method that works for you and you know your metric conversions based on that method, great, right? Because most of the questions you're going to get about this on the campus exam are going to be questions where you are just choosing from a list of different choices and multiple choices what the correct answer is. I won't need to see the work that you do, but this would be the basic way you would use the dimensional analysis. You've done something like this before, right? Let's try it with grams to milligrams. I need to know how many milligrams are in 5.5 grams. 5.5 grams. I need my conversion factor here, right? In order to get my milligrams. What conversion factor would I use here?
1,000.
1,000. So I have 1,000.
On the bottom.
One on the top. There we go.
Yeah.
1,000 milligrams. Because I need to cancel out my grams, grams goes on the bottom instead. Right? And now I'm multiplying this number by my 5.5, 5,500 milligrams. Okay. Now, what if I didn't go directly to a base or didn't come directly from a base? Technically, you can make this into a multi-step process. As an example here, let's imagine that I'm going from, I'll put it atop here, 34.5 centimeters rather than meters. Let's say I want to convert to millimeters, right? Now, yes, there are quick methods where you can go directly from centimeters to millimeters, shortcuts that you can use if you're familiar with them. But I'm going to use the dimensional analysis just to show how you'd use that multi-step process. You have your first step, which we already show, the 34.5 centimeters. Multiply that by your conversion factor. That's it. That's not an M. Okay. Okay, so at this step, I would have converted my centimeters to meters, but I don't want meters. I want millimeters, right? So technically, can't I convert from meters now to millimeters, knowing that conversion factor? And how would I set that up? What would go on the bottom here?
1 meter.
1 meter. What would go on the top?
1,000 millimeters.
Perfect, 1,000 millimeters. Okay. Meters cancel out. The units I will be left with are millimeters, and then I just have to do the math. 34.5 divided by 100, multiply by 1,000. You could take some shortcuts there as well in terms of the math that's being done. But in the end, what you should calculate, just so you can self-check, is 345 millimeters. Okay. What do you think? Pretty basic stuff? Pretty straightforward, what we're asking of you here for this review. But things can get kind of complicated, especially when you get to the really small or the really large units, but especially the really small, like the pico and the femto for the prefixes, and being able to convert back and forth, because there's so many zeros there, and remembering how many zeros are related to a trillionth or a quadrillionth can get a little tricky. So I'm going to show you here is just a quick method that you can use to convert back and forth within the metric system that you can choose to use on the exam. You can choose to use some other method that you've learned in the past, or just the dimensional analysis. But it's something that I find very useful, and have come to sort of make it a habit of writing it down whenever I'm doing these types of conversions by hand. And that's called the King-Henry slider. And this would be the basic King-Henry slider that I'm showing you here on the screen. And it's a mnemonic device that you use. And if you draw it in this fashion, using each one of the letters to denote your prefixes, and each of these prefixes showing us a unit of 10 difference, 10 manifold or magnitude difference between our prefixes, then we simply know where to move our decimal point instead of doing all of the calculations in order to convert within the metric system. This here is the basic King-Henry slider. It's not useful to us. It starts with K for kilo, and then H for our hecto, Henry, D for deca, for dyed. Here, rather than base, they're using U for unit, which is fine. But notice on the other end of our King-Henry slider, we only go to M for milli. And that's not going to cut it for us, because in this class and for your metric conversions on this quiz, you want to go all the way to femto. So here's our modified physio King-Henry slider. Rather than King-Henry dying here unexpectedly drinking chocolate milk, we're going to say that King-Henry died by drinking chocolate milk under 9 pink flamingos. But what is important here is there are dots. If you see these dots here, 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 and let me squeeze them in on the end here, right? When we read this out, these will be our dramatic pauses. King-Henry died by drinking chocolate milk, under, 9, pink, flamingos. Each one of those dots is a space holder for magnitude of 10 difference. The metric system here jumps from hundreds to thousands, thousand-fold difference. 10 times 10, and then our next unit of 10, right? 10 times 10 times 10, thousand-fold difference. So we account for that with these space holders here. Rather than using unit in our King-Henry slider, we're going to use base just for consistency. So died by drinking rather than died unexpectedly. But now that I have this sentence written out, something I might write across the top of my, my scrap piece of paper or my exam when I'm doing my metric conversions, I can now use this to determine where my decimal point starts and where I should move it and how many decimal places I should move it, okay, in that direction. So it tells you what place to move the decimal. It tells you what direction to move the decimal. We're going to count each one of these boxes here as a base of 10, magnitude 10, and each dot as a factor of 10 as well. Key is we don't count our starting point. Never count the starting point. So let me show you an example of that. We're going to use the same questions we used earlier with the dimensional analysis, but now we'll show how we get the same answer with the King-Henry slider. How many meters are in 34.5 centimeters, right? We start with our 34.5. There's our decimal point right there. And we find centimeters here on our King-Henry slider. Centimeters is denoted by our chocolate for our chocolate milk, right? There's our starting point. We start here. We ask, where do we want to go? We want to go to meters. Keep in mind that meters is a base, and so it's denoted here with the by for base, meter being an example of that. So this is where we want to go. And we want to move from centi to the left until we get to meter for the base. Rule being we don't count our starting point, but we count each of these blocks after it as a magnitude of 10. So deci and meter, right, our base. We move 2 decimal points to the left. That's what we do. Take that original number and we move 2 decimal points to the left to get this number here. 0.345 meters. Okay. Let's try it with the milligrams to grams that we see here. We want to know how many milligrams are in 5.5 grams. Well, grams is a base, so we start with our base, gram. We want to convert to milli. So we start here and we want to end up here. We're going the opposite direction now with our decimal point. Rather than moving it to the right, we're moving it to the left. And we're moving it 1, 2, 3 decimal places to the left. Remember, we don't count our starting point. Here our gram, but we count deci, centi, and milli. 3 decimal places to the left. So we take that 5.5 and move our decimal point 3 places to the left, and we get 5,500 milligrams. Okay. We're going to try a more difficult one in just a minute, where we're going to employ now these dramatic pauses. But first, let me point out that not only do you want to be able to do these conversions, like I said, dimensional analysis or just a quick method like this is just fine to use so that you get your conversion. But then once you have that number, I might say, I don't want the answer in that format, this being what's called the standard notation. I want it in the scientific notation. And maybe all of your choices for your multiple choices are in scientific notation. So you might have to go one extra step and then convert your answer to scientific notation in order to choose the correct answer from your choices, your choice bank. So let's quickly discuss what the difference is between scientific and standard notation. What we are just looking at is standard notation. Scientific notation is the notation that's based on powers of base 10. And this is the format we would be using, right? Capital N times 10 to the exponent x, where n is a number that has to be greater than 1 but less than 10. Right? Greater than 1 but less than 10. And x represents the exponent, which tells us something about the decimal places and the placement of those decimal places compared to what would be the standard notation. Why use this type of scientific notation rather than the standard? It can be very concise, and that way it's useful. It's easier math to do without your calculator, right? In terms of it being concise, it's easier to write, say, something in femtometers as scientific notation with all those zeros that would normally be there rather than standard notation. And that is going to be an example we're going to work on, right? So it's easy enough to write this scientific notation, knowing that we need to keep the number itself greater than 1 but less than 10. But one of the biggest points of confusion is whether we should have a negative exponent or positive exponent. This is the general rule we use here in terms of how we decide whether the exponent should be positive or negative. Sometimes you might feel it's just intuitive. You understand that there should be a negative or positive exponent. Sometimes I have to stop and think to myself, wait, should that be positive or negative, and have to double check. And this is generally what I do to double check. I ask myself, how do I have to move that decimal point to arrive at my original number? And key here is not the original number being what you had before the conversion, but what you had written for the standard notation after conversion, right? The original number after conversion, if what you're doing is converting. Once again, sorry for the writing, right? How must you move the decimal point to arrive at the original number you had after you did the conversion? If you would have to move the decimal point to the left to get back to that number, you would have a negative exponent. If you have to move it to the right, you would have a positive exponent. Let's practice a few so you understand what I mean when I say this. I'm going to go back to the previous slide here. Let's take that 0.345 written in standard notation, and let's write it now in scientific notation. You need to take a minute, think to yourself, how would you write that down? It was so how do I make that number 0.345 greater than 1 but less than 10? Where would I have to move that decimal?
3.45.
3.45. Great. 3.45. Let me move it over a little bit. 3.45. But now that I moved the decimal, now I need to add my exponent. Okay. What is the exponent that I use there?
-1.
-1. Okay, -1. Now, it should be enough to understand that it needs to be 1, whether it's negative or positive, simply because I moved this decimal 1 decimal place, right? So there should be a 1 there. To get that 3.45, I moved it 1 decimal place. Then the question is, should that be a positive 1? Should it be a -1? What should I take into account to understand that? Well, let's say we didn't know whether it should be positive or negative. We just had 1 there. We're trying to figure that out. Go back to this here, 3.45, and ask, how do I need to move that decimal point to get back to this number here, my original number after conversion? I would have to move the decimal point 1 space to the left to get back to 0.345. Right? And whenever I have to move a decimal point to the left to get back to that original number, my exponent needs to be negative. So this needs to be negative. Takes a little bit of practice. Let's try converting this one here, the milligrams, 5,500 milligrams. 5.5, that makes sense, right? It needs to be a number that is greater than 1, less than 10. How many spaces do I have to move the decimal point to get to that 5.5 from 5,500?
3.
3. Should that be a -3 or +3?
Positive.
+3, right? +3. Let's just check to make sure we're correct with that. It is correct, but let's check. We have this 5.5, and we ask, how do we move the decimal point to get back to that original 5,500? We would have to move that decimal point 3 spaces to the left, to the right, in that direction, to get back to our original number of, after conversion, of 5,500. So that makes that that exponent positive. Okay. And if it helps, all we're really picturing here is where the positive and the negative is along a number line. If this was 0 in the center and we move to the right, we're moving towards positive numbers, to left to negative numbers. Okay, so before we end this recorded section and take a 10-minute break and start up the next one, let's just try this one here. Let's try to convert 1 millimeter to femtometers using our King Henry slider. So we want 1 millimeter converted to femtometers. And once you convert it, write it not only in standard notation, but then write what that would be in scientific notation. Now let's see what you come up with for an answer. So take a minute to do that. And if you get an answer, you can put it in the chat window. See what kind of consensus we get for scientific notation. All right, looks like we have a consensus here, which means some of you have caught on to what we do with the dramatic pauses. Let's just review that quickly together, how we would use those dramatic pauses. And this is an excellent example because we have to go from millimeters, start here, milli. We want to go all the way to femtometers, which is here. So we're moving our decimal point to the right. We have to understand how many places we're moving that decimal point. We don't count our starting point, which is milli. We count each one of these dramatic pauses, the dot dots, as 1 decimal point or magnitude of 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We'd have to move the decimal point 12 spaces to the right. And we could do that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's a lot of zeros. That gets pretty cumbersome. So yes, it would be easier to write this in scientific notation, and the answers you're giving me here in the chat are right on, that we need a number that is going to be greater than 1, but 1 or greater than 1 and less than 10. So 1.0 times 10. We ask ourselves, well, how many decimal points do we have to move to get to that large number? And that would be 12. Should it be positive or negative? Well, what direction do we have to move this decimal point to get to this very large number that we have here? We would need to move it 12 places to the right, which would make this exponent positive along a number line rather than negative. So it should be 1 times 10 to the positive 12. Okay. So just keep in mind that might be asked of you, a 2-step process where you do a conversion, and then your answer bank is non-standard but scientific. And so you will have to know how to convert back and forth between standard and scientific. Okay, so I'm going to stop the recording. But I'm not going to stop the session.